recording is going to start. Okay, yep. So recording should be on, and I switch over to share screen. Okay, good. And here is the screen. Can you see the screen, by the way? Because I'm pretty blind here. Yes, excellent. Yep. So, technology works. And please keep your microphones muted, because otherwise I go mad. And I think you need to record your attendance on Moodle. Is that right? So please head over to Moodle and record your attendance, because I think that is one of these timetable sessions in the BI600 module. Exactly. Good. Excellent. And while people are doing that, let me just give you a sort of, how shall I say, an idea of what this research project actually is. And it really doesn't matter whether you are doing a lab-based project or whether you are doing a dissertation or any of the other projects. What the intention of the final year research project is to give you a really good feel for what research actually looks like. And as I said, this could be lab research, but it could also be a very important aspect of research in general, i.e. going through literature. And the most important thing, I would say, the most important thing of this BI600 is that you learn how to ask questions and how to actually manage a project. That is the most important thing. Now, people say to me, when we are doing lab-based projects, I'm so scared that I don't get any results. Is that actually a concern that people have, if they are doing a research project, that they don't get any results? Is this one of the concerns? Or am I just barking up the wrong tree? Yes. Not all the time, but... So I'll tell you what, because this is a fear that I want to completely debunk here. If you don't get good results in your lab experiments, then the important thing is not that you say, oh my God, I didn't get the right results. The important thing is that you demonstrate you have thought about what is going wrong or why didn't it work. Just to give you an example, a few years ago, I supervised a project where basically everything that potentially could go wrong went wrong. And at one point, we even celebrated if an agarose gel set. So desperate were we, because, as I said, all sorts of things went wrong. We discovered that our mutants were all wild types. We discovered that the protein that we were looking at was of the wrong size. We discovered all sorts of weird and wonderful things. And the student said, you know, I am truly and royally compromised in my ability to write up. And I said to him, no, you're not. You have got lots of stuff to write up. You can say, right, I tried this and it didn't work, so I tried this. So what these projects are, and this is not just a lab-based project, what you are supposed to do in this project is to tell a nice, coherent story. Even if the story doesn't have a happy end, you should be able to talk and tell a nice story. What you have done, why it didn't work, and how you try to think about what is going on. So, and because you will be working for the next, I think, 4 months or so on your project in one shape or one form or another, you will be the experts. It's not that the academics who are supervising you are the experts. You will become an expert in this field. Last year, for example, I supervised some dissertation projects on Parkinson's disease, on sleep and memory and things like that. I'm not an expert in that, but I was really curious to learn from you guys. And if you can teach me, then you will get a first-class mark for that. As simple as that. So please don't be worried. Be excited about it. So what I want to do with you today is build up a little bit on what we have started last time we spoke in as a sort of a feedback for one of the practicals. And I know that some people found the practical probably too easy, but then the analysis of the data quite challenging. So last time we were talking about measurements. So measurements. And the last time you just pipetted some water, I think, and you had to do some measurements. And really what I wanted you to get out of that is the importance of measurements. And here's the difference between a scientist and a good scientist and just simply an amateur, a layperson. A scientist, when they do measurements, they will always report three things, or basically two things. One is the thing that they measured. So that would be the measurand. That's one thing when they do the experiment. They measure something, they get the measurand. What are the two other things that a good scientist will always report? So that's the number. So let's say 140. What's the other thing that everybody needs to report? Conditions, units, yes. So we need plus units. So we've got one more thing, plus units, absolutely essential. What else? Thank you. We need to report the uncertainty. We need to report the uncertainty of our measurements. And the mean, for example, what George says, that would be, for example, our measurement here. But the uncertainty of our measurement, that is absolutely crucial. Because, as I said last time, it can decide over life or death. When you look at the R factor for COVID, if the uncertainty is so big that we can't really make a decision, then we are running into problems. Usually, you will take samples. You will take a sample, so you won't rely on a single individual measurement, for which you will, as George rightly says, you will calculate the mean. And the way you would report that would be the mean plus the unit. And if you are working with samples and you're not, how shall I write that? Not close to the to limitations of your equipment, limits of the tools that you use. And usually you won't be close to these limits, then your uncertainty will be predominantly derived by the sample uncertainty. And some people also call it the sampling error. So that's the main uncertainty when you are working with samples plus sample error. And after all these weird and wonderful calculations that you did the last time, maybe people have spotted that as long as you are not close to the limits of the tools that you're using, you can report a result if people want me to upload this onto YouTube, but I will upload it onto BI600. Since it is recorded, it will be uploaded to BI600. So what you would report is X bar, that's the mean, unit, plus, minus, and people might have spotted when you did the measurements, it will be roughly 2 times the standard error of the mean for your sample. So this is the sample standard deviation. And this is the number of observations. This is how you usually would report the results. The number 2 just simply comes from an expanded uncertainty, because you usually will be using a normal distribution, and that gives you a 95% coverage of your results. Does that make sense? So if you have, for example, let's do a practical example. We measure mice 14, 16, 18 centimeters long, our little mices. We can calculate the mean for the sample, which would be, what is the mean in this case? What? Bananas. Ah, thank you. 16 centimeters, so that's the unit. Plus minus 2 times, what's the standard deviation? Daniela? This is exactly one of the problems that I'm very unhappy about, that people do all sorts of weird and wonderful things, and they fail to report what they are actually doing. So they leave it up to the reader, and I think that's criminal. And Amelia is right. The standard deviation is 2. So we would report this, our measurements, as 2 over square root 3 centimeters. The square root 3 is because it's the observation. So we have, what is that? What is this uncertainty? Can somebody quickly do the calculation? 2 times 2 divided by square root 3. What does that give us? Mm-hmm. 2.309. 2.309 centimeters. Big problem with that. So if we write 16 plus minus 2.309, oh wow, Amelia is really pushing the boat out with God knows how many digits. An uncertainty should only be given to one or max two significant figures. Significant sig figs. So in this case, we would report this to two significant figures. That would be 2.3, right? And what we now need to do is we need to adjust our measurement so that it has the same decimal place. Same decimal place. So the first step is we calculate the uncertainty, this bit. We then reduce it to one or max two significant figures. And in the third step, we adjust the decimal places for our measurement. So in this case, it would be 16.0. And we would report our result as 16.0 plus minus 2.3 centimeters. And as Daniela rightly pointed out, we would is by we have a coverage of factor 2 and 95% coverage, 95% confidence interval, and we used a normal distribution. And that is how it actually, this result should be reported. This is what people need to report. You will never see that in a journal because it's crap and the editors don't pay attention to that, but this makes it absolutely clear. This is what has been reported. And of course, you would see in the description also that n equals 3, for example. Yeah. So that is how you should report it. And that is what I wanted to get you out of last week's practical. What is in the brackets? Okay, K is the coverage factor, because if you did the measurement calculations, and again, here, this 2 comes from, we are using a 2 sigma interval of the normal distribution. When we do that. And we know that if we are in the 2 sigma range, let me try to do a nice normal distribution. Here we are centered around the mean, or in this case, our sample mean. We know that we have this case. This here is 1 sigma, this is here another sigma. So in this 2 sigma range, either side, so this range here, how much of our data are in there? In this shaded area, 95%, absolutely right. So we know that when we report our data set like that we have 95% of our data reported in this way. What if we are dealing with data that is not normally distributed? That's a very good question. You would usually then use a different coverage factor, and you would need to indicate that you did not use a normal distribution. So you could say, for example, K equals 1.7, 95%. And let's say, what is 1.7? Beta distribution. Whatever beta distribution is. Yeah, something like that. But you need to indicate that so that people really are clear about it. Does that make sense so far? This is the true way of reporting your results. And in the last practical that you did, when was the practical? That was last Friday, Thursday, Friday. We expanded that a little bit because while you did something here in the first practical where you just simply calculated the mean, I would describe this as a one-dimensional measurement. You just simply had to calculate the mean and do a little bit more with resolution, basically to see whether you're close to resolution and things like that. Last week, we did actually a two-dimensional measurement. How come? Because what you were asked to do last week was not just take one measurement in a way, you actually produced a standard curve, very often this is also referred as a calibration curve. And this curve, let's draw it like that. So you measured different points. These were the concentrations. So that was the concentration of your paranitrophenol. And here was the absorbance. Did you get a reasonable standard curve? Did you get something like that, like I've drawn? Did people get that? I'm glad at least one of you got it. Did other people get it as well? You see, that was one concern. I've sort of designed this practical more or less from scratch, and I wasn't quite sure whether it will give me a straight line. Were all the points that you measured on a straight line? Not as neat. Ah, that's good. That's good. Thank you, Astrid. That's that's very nice that it wasn't totally on a straight line, but it looked pretty much something like that. Fantastic. That was my main concern. Now, what you are actually doing here is you not only calculated your samples in one dimension, you had two dimensions, this and this dimension. It is still a sample, because you could have repeated that experiment. If you had repeated the experiment, so say 4 times, would you have got exactly the same data points? If you had repeated this experiment 4 times, would you get exactly the same data points? And with exactly, I mean absolutely exactly. No. Are you doing something wrong then? Is there a problem that you didn't get it the same? Why would you get, you're absolutely right, you would not get the same data point if you repeat it 4 times, not exactly same numbers. And the reason why you would not get exactly the same numbers is called uncertainties in numbers, yes, or it has a technical term, standard error. Well, not a standard error in this case, it would be a sampling error. Or combine it, let's call it sampling uncertainty. It's just simply the numbers can fluctuate slightly. And as I said, sampling error is like herpes. It is just simply there. There's nothing you can do about. You will always have sample error if you take different samples. Nothing else you can do to avoid it. Sampling error is there, is a matter of life. But because you are now in 2 different dimensions, you can see that we have 2 different sampling errors. 2 different sampling errors. One of them affects the gradient, and the other one will affect the intercept. Because if you've got a straight line for this trend line or line of best fit, so the line of best fit, as any line would be, what is the line of best fit, or line, equation for a straight line? What was that? Y equals mx plus c. Thank you. Mx plus c. So we have a sampling error in the gradient in M, and we have a sampling error in the intercept C. And because we have this equation, we can define our line of best fit just simply by M and by C. But these 2 things gradient and intercept have actually sampling error in them. And there's nothing we can do to avoid them. We will have the sampling error in it. So how do you find the sampling error? And why do we need to know? Well, for example, we know that if you, for example, do, oh yeah, let's do that. Ha, that's a cool one. Let's do a line-Riverberg plot. Do you remember line-Riverberg? Enzymology? The horrors. Ah. So in a line-Riverberg plot, we actually plot, this is related to the Michaelis-Menten equation. We plot 1 over the substrate concentration on the x-axis. What do we plot on the y-axis? 1 over... Ophelia already got it, yes. So we would plot 1 over the rate of the enzyme, and we would get a straight line. Does anyone remember what this point here is? Obviously, that's the intercept. What was this point, the intercept, in the line-Riverberg plot? Vmax? Is Ophelia right? There's a question mark I can see. Absolutely right. Don't be sort of show self-confidence. Never put a question mark down. Just say it's 1 over Vmax, right? This actually would be 1 over Vmax. This point. One of my colleagues gave me this advice because I used to do question mark. One of my colleagues gave me the advice or told me his motto. He said, frequently wrong, but never in doubt. And I think that's something really good. So here we've got 1 over Vmax. The gradient for this, and I drew it like that. Can anyone remember what this was? And please without a question mark. Excellent. Excellent, guys. It is Km over Vmax. And this point here, down here, this one here, what was this point? Yes, -1 over Km. And this was one way that I think you were taught how we can find the enzyme parameters. And these enzyme parameters would be Km, Vmax, and of course Vmax over Km. Now, the big thing is here, if we have an uncertainty in our gradient, so that is M, or, oh, sorry, that is the intercept. Let me remove that. That is C. And also here, that's the gradient. If we have uncertainties in M and C, our straight lines could look very different. And in fact, a student, I think 2 years ago, contacted me because they did the line Riverberg plot, and they had data like this. Not particularly good, but anyway, so they did a straight line like that. And why did they panic? Why do you think they panicked? Absolutely right, George, because they found that the intercept is negative. They discovered the intercept is negative. What does that mean? Well, if that is 1 over V max, then surely 1 over V max is negative, or in other words, V max is negative. OMG, what is going on? You can't have a negative V max. It's not possible. So I tried my very best, and that was over the Christmas holidays. I tried my very best to talk the student down again. Don't panic, because what you are experiencing is this is a sample that you have. Surely it is a sample. And the reason that you see a negative intercept here is because of the uncertainty in your sample, or more specific, uncertainty in intercept in this case, and probably also the gradient. The only way to overcome that, of course, is to say, right, my intercept is basically this value, this intercept measured, plus minus the uncertainty in it. And then the student would most likely, had they done the calculation, would have seen that this uncertainty puts the intercept probably in a range like this here. Yeah. That means there would also be positive numbers, but then again, it would put a big question mark behind the whole thing, because if you get something in the negative range, it actually indicates that there might have been some problems. On its own, if it is just negative, then it just indicates that it's total nonsense. But with the indication of the uncertainty, you would get an indication that, yes, there is something, hopefully there is something positive in it, but there needs to be, the result needs to be taken with care. How do you find the uncertainties? How do you find the uncertainties of gradient and C and the intercept? In Excel, you have the function in the data tool pack. The function regression. because this is a linear regression line. And if you do the regression analysis, and I think there is I sent you the link to YouTube videos, you can very easily find the uncertainties for both for M and C. And you can even get, so these are the standard errors that Excel spows out. Standard errors, and you get also the extended uncertainties. These are the 95% confidence intervals. So when you do a regression line, like you did in your experiment, where is it? In this experiment, what you do is Excel regression, and you get the standard uncertainties and also the extended 95% uncertainties for your measurements of the gradient and the intercept. If you don't have Excel installed, you can do that also in other programs, for example, in Google Sheet with the line est function. And I think, did I post a YouTube link to a YouTube video for the line est function? Yes. So line est is a little bit less convenient because you have to remember what the different entries are, but the line est function will usually, if you do it properly, you will get gradient, M and C, and in the column underneath, you get the standard error for the gradient and the standard error for the intercept. So you can get the standard errors and then nicely figure out then what the 95% confidence intervals are. So if we are going back to the practical that you did, here you plotted the concentration, here you plotted the absorbance, and let's say you got something like this for the line of best fit. You can actually calculate what are the uncertainties. So you can calculate M plus minus the uncertainty and the intercept plus minus the uncertainty. Now, how does that actually impact on what you wanted to do? Because what you wanted to do is you had an unknown sample. I think, am I right? You did have an unknown sample. Yes. And the usual thing that you would do with an unknown sample is you just simply measure the absorbance. Or rather, you would measure the mean of the absorbance. Did you do that? I think you did it in triplicates. Yeah. So you would just simply say, right, I measure the absorbance of my unknown sample. And let's say I measured this value here. And in order to find the concentration of that, I just simply read it from my standard curve. Is that how you did it? Reading from the standard curve. Yep. So you basically got this value here for the concentration of the unknown sample. Easy, simple. Everybody does that. But hang on, there is a problem. Because if there is an uncertainty in the gradient, and if there is an uncertainty in the intercept, just simply because you've got samples here of your measurements, your gradient, your line of best fit could look like, for example, like this the next time you measure it. Or it could look like this the next time you measure it. And please keep it muted. Thank you. And each time you get a different value for your unknown sample. Does that make sense? Because you use a sample for the standard curve with uncertainty, you might get a different value for your unknown sample. So therefore, we need to find out what is actually the mean of the unknown sample plus minus the uncertainty of this mean. And I don't want to go into the heavy maths. I think I posted the links of how you determine that. But what you find out is that you can actually determine what is called the confidence interval for the line of best fit. Let's say this is your line of best fit with the data points here, 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 here. And what you see is, and I hope I get this right, what you find is a range like that. Yeah, that doesn't look too bad. This range here, and let me do that in a nice color. This range here, this is the confidence interval for the line of best fit. So instead of saying I have a very well-defined line of best fit, I indicate that with this range where I say my samples indicate that the true best fit line must be in this range. Although I don't know exactly what the range is, what the best fit is, but the line of best fit is in this range. In this range. And now reading an absorbance of this line gets a completely different meaning, because the way you then do it is you say, okay, here is the absorbance that I measured. That's the mean of the absorbances that I measure. And instead of what I've done previously, where I just went over to my line of best fit and then went down, what I now need to do is, in order to find the uncertainty, I go there and say, okay, my line of best fit is limited by this point, so I read it here. Or on the other side, it is bound by this point here. And what you see is, it's no longer a single point like it was in this case here. With this range of best fit, no longer a line of best fit, with this range of best fit, I get an uncertainty estimate. Uncertainty estimate for my observation, for the mean. Does that make sense to you? Brilliant. Calculating these values here. I posted that in the video from my colleague from Oxford University, but I fully appreciate that this is not something for the faint-hearted, and I would not necessarily expect you to do that in your project or something like that. Instead, what I have done to make life easier for people is I have written a program that can do this calculation for you. And I think you've got the link to that. So that is called Estimate the 95% Confidence Interval for Readings from a Calibration Curve. It took me a while to figure that out, how to write that program, but I'm pretty sure it is correct. And what you can do is you just plonk in your numbers, the X values, the Y values, and the unknown samples. Yes, I know, I'm good. You can plonk in your unknown samples, and it will then come up with the uncertainty for your observed data for the unknown samples. And this should hold true basically for whatever measurements you do, as long as they are within reason. Now, of course, what you see is with this range for the best fit, it is curved. So if you go outside, if you go away from basically in the middle, it is the slimmest. Here is the slimmest, but if you look at outside, it gets bigger and bigger. And also here, it gets bigger and bigger. That is why you try to do what you try to do when you measure an absorbance, you try to measure it in the middle of your line of best fit. So you will always aim to get this reading for the unknown sample so that you're not at the extremes, not here or not here, rather in the middle, because there the confidence interval is the smallest. If you did it, for example, here, if you had your mean up here, this one here, and it gets a little bit wild. Let me just choose a different color. If your mean was here, what you see is your interval would be much larger. So that's why we try to measure things in the middle of a line of best fit. Does that make sense? I will post the link to this program in this chat and also on Moodle. If you got that, you don't have to worry about your final check because you can read from standard curves. Are you happy with that? Was that useful? In this case, I shall say thank you very much. I leave you in peace, and I hope you have a great week and enjoy your start to the projects. So thank you very much, and don't do anything I wouldn't do.